So the next topic we want to look at is partial derivatives. And remember that we are still have not found a way to find tangent planes. Remember that my first goal in the class was giving a surface. I want to find a tangent plane. We know now how to find equations of planes. We're this close to be able to find tangent planes. And that, what we need, the last push we need is partial derivatives. So we're going to talk about what are partial derivatives, derivatives in different directions. How do we interpret those? What are higher derivatives? So just like we had the second derivative, third derivative in one variable, what are they? And then I'm going to give you one example of partial differential equations, which is like how we describe nature and many other things. So what are partial derivatives? We have functions. We have graphs, some graph of, say, a hyperbolic paraboloid. And then the partial derivatives are going to be, I'm going to intersect, for example, with this plane and see what is the line that I get there. I'm going to draw a line that goes through a point. And then I want to know what is the slope of that line. I'm going to use those slopes to come up with the equation of the tangent plane. I can do that in that direction, or I can do this in another direction. I can also look at this direction here. I can look at the line that passes through that tangent over there, and then I can draw the plane where that line is. And those two lines actually define a third plane, which is going to be the tangent plane. But what I want in particular are the slopes of those lines. And those slopes are going to be our partial derivatives. Okay? So what are the partial derivatives in this very case? So if I have z equals x squared plus y squared. And let's see what happens in the x direction, so in the xz plane. In the xz plane, for example, the graph is when y is 0, I get z equals x squared, so it's a parabola. So I know what the derivative is at any of these points. I know what the slope is. The slope is the derivative. The slope, this is the function z equals x squared. So the slope right there will be z prime, which is the derivative with respect to x. So it is 2x. Okay. So at the point, at that point, x naught, this line right here is the line that goes through the point y minus y naught, x minus x naught, and I know the slope as well. The slope will be 2x naught, and I in fact also know what y naught is. It's the z value in fact here. So it's the line z minus z0, but I know what z0 is. It's x naught squared. Okay, so I can actually compute the tangent line exactly there, and if I draw my graph here, I can figure out exactly, at least in this line, what every single derivative is given by 2x. Okay? So I want to know what is the derivative at any point and in both directions, in the x direction and the y direction. So I actually find the derivatives using the same limit definition that we did for one variable. Just to remind you, if I have one function of one variable, the derivative at x naught, say, was a limit as h goes to 0 of f of x naught plus h minus f of x naught divided by h. So if I want to know now if I have a function of two variables and I want to know what is happening at x naught, y naught, I'm going to have several possibilities. But for example, what is the derivative? We're actually going to call it, because it's a partial derivative, the symbol is a little bit different with respect to x at x naught, y naught. We'll have several notations for this, and I'll talk about that next time. I'm going to do the same thing. In the x direction, I want to know what happens when the x changes and the y is fixed. So I'm going to think about this function as if the y was just fixed and it was just a function of x. Then I can use my old definition, and this is going to be f of x naught plus h with y fixed minus the value at x naught, y naught divided by h. So this is going to be how we define one directional derivative, the derivative in the direction of x at any point. But you see that this is exactly the same definition we used, but I'm just restricting my function to look like as if it was a function of one variable. So the derivative rules that we learned before apply here, except that when we're taking derivatives with respect to x, we're just going to think of y as a constant. And when I take derivatives with respect to y, I'm going to think of x as a constant. So we'll do a lot of examples of this next time.